Good morning, mathematicians. It's ASMR coffee time. If that doesn't make you want to start doing some mathematics, I don't know what will. I don't know what will. Nice. And I get to hear the playback. Nice. If that doesn't make you want to start doing... good morning, Matthias. Good morning. I don't even remember what I was yapping about yesterday. What was I yapping about? Let me open up OneNote. Let me open it up. Oh yeah, we were talking about, I was looking at that paper that I came across. Yeah. Yeah, also I did realize that getting this, this thing from the module thing, I don't know why I got stuck on it before. It's actually pretty straightforward to show. Well, things are like that sometimes. So, expect new videos about that eventually. And eventually, I would like to have that series cover the Merida theorems, which covers equivalences between categories of modules. Let's delete some of these extra things I don't need here. Yeah, delete that too. So, and eventually, I think I've talked about this before, but I would really like to understand, well, maybe I can just bring up the paper. Why don't we do that? Yeah, so in this paper, well, there's a few things that happen in this paper, but one of the things is that they prove, well, they basically recover a scheme from its category of quasi-coherent sheaves. So as a very special case, right, so if these are quasi-separated schemes and the categories are equivalent, then the underlying schemes are isomorphic. Seems related to tensor triangulated geometry. I don't know about that, but it certainly could be. Yes, but then this is the theorem that I'm very interested in. So if X is a quasi-separated scheme and the automorphism class group, then the automorphism class group is basically the automorphisms of the underlying scheme, of course, through like your push forwards or your pullbacks. Oh, this the pullbacks may be the more natural one. Those, of course, induce autoequivalences, as does your Picard group. So, sorry, what was I saying? Yeah, so that means as a special case for commutative rings, we recover. I sort of stumbled on this paper because I was asking myself about the following question, like, can we understand the group of isomorphism classes of autoequivalences of the category of R modules? And in fact, this tells us that yes, it's just going to be, well, in the case of a commutative ring, it will be the Picard group semi-direct, the automorphism group of the ring. But now my question is, what about R non-commutative? Actually, there's another question I have too. So, of course, their paper resolves it in a much more general case of sheaves on schemes. But then I wonder, is there like, as a means to maybe developing these results for non-commutative rings, is it possible, is there a way to prove these results just like purely algebraically in the case of modules? I don't know. If anyone wants to think about that with me. Oh, interesting. And there's also this variant that takes into account the tensor structure. Quasi-arbitrary scheme between the discrete category of morphisms and the category of co-continuous symmetric monoidal functors. Oh, okay. So I mean that, what would that would have to have, that should also have, that should also have a module theoretic analog, right? If you looked at like the discrete category of ring morphisms, then it should give you co-continuous symmetric monoidal, well, in the commutative case, symmetric monoidal functors between the categories of modules. But then, of course, it becomes more interesting. We lose the symmetric, or no, what am I saying? Yeah. There's some approaches to non-commutative algebraic geometry based on replacing schemes by their categories of modules. Yes. So I'm aware roughly of this idea. I am aware roughly of this idea, but I just don't know. I mean, hey, look, they even cite something about non-commutative projective schemes. But when I've gone and tried to look things up, I don't know, my eyes just glaze over, and there's just like a mountain of detail that I just don't understand. And then I'm like, well, maybe I should work on my thesis. Yeah. There's another paper. I can't remember the name of the other paper. They take a certain approach here. Oh, no, I guess both papers take the same approach. Right. They form... Well, maybe this is the same thing that happens. Maybe this is the same thing... I don't know. So, like, they form a scheme out of the category. Apart from being interesting in its own right, reconstruction is important for the vision of non-commutative algebraic geometry, in which abelian categories are regarded as non-commutative schemes. Yeah, so I guess this idea goes back to Rosenberg. How many times have people come here pretending they know stuff to me and obviously don't know anything? Very rarely. Only once, I think, actually. Yeah, only once. That was the era where we had well, he went by different names, right? Arcturus. He also went by Mustafa. Ibrahim used to show up here randomly and, say a bunch of nonsense. I mean, in his defense, he was like 13 years old. But I don't know. I wasn't. Well, I was probably posturing in different ways at that age, but I wasn't just making up nonsense. Other than that, everyone who showed up to office hours has like legitimate questions, and is curious and open to learning. So, which is good. You just did this with the non-commutative geometry thing? Well, sorry, what do you mean you just did this with the non-commutative geometry thing? You proved the theorem I'm interested in? That'd be exciting. Isn't this how everyone feels on a daily basis? How so? How do you mean? I'm not sure I understand the question. What am I doing? Well, right now I'm staring at a paper on some algebra / algebraic geometry. Yeah. It is some fancy math, but hey, I'm also here to answer simple math questions too. So if people have simple math questions, except for the ones I don't feel like answering, then I don't answer those ones. Yeah. But yeah, I mean, I was looking at this paper, and yeah, it's not clear to me how to say take the approach used in this paper. And it's not clear to me how exactly to go about doing that, precisely because they go back and like it's this weird thing. They're like, oh yeah, so we'll build a scheme out of this category, and it's like, oh, okay, cool. But then it's like, well, how do I apply that same and the idea is we recover like the original scheme, but then it's like, well, how do I apply that to the category of modules where I know it came from like a ring that wasn't commutative, and it's like if I just think about the abelian category as the scheme, well then it's like, but I'm stuck at the abelian category. Like I want to somehow say something about those equivalences. I don't know. Do I have any good geometric intuition for working with Witt vectors? Not at all. I've looked them up before. I don't even remember what they are. Infinite sequence of elements. Oh. The Witt vectors are just ZP? Oh, well, there's your problem right there, Arad. They have a highly non-intuitive structure. I like how they even have a reference. They're like, hey, if you don't believe us that it's not intuitive, you go read this PDF. Depends on infinite recursive formulas. Jesus. Well, then it's obviously fake and wrong because we can't put it on a computer. I'm only half joking. It's supposed to be like a mixed characteristic version of formal power series. The main idea is that instead of the p-adic expansion to represent an element of ZP, an expression using the Teichmuller character can be considered instead. I see. I see. Interesting. So we expand them out in terms of roots of unity. Uh-huh. Yeah, that's kind of freaky. The non-trivial additive multiplicative structure comes from using this map to give this structure. Yeah, I definitely can't. I definitely can't help you with. I definitely can't help you with visualizing this. Oh, there's a detailed, motivated sketch here. I don't know how much that helps. I'm not sure how much of a visual thing this even is, right? I mean, expanding something in a basis of roots of unity, and then I can definitely believe the arithmetic gets kind of wild. Oh, ghost components. Ghost map. Hell yeah. Hell yeah. That sounds so badass. The ghost map. Might have to study these things at some point. Who am I kidding? Not taking a commutative ring to its width vectors is a functor from commutative rings to commutative rings. Oh. It's representable. Interesting. Yeah. Unfortunately, I can't help you. There are things that have popped up time and time again. And I've looked at this wiki page probably a million times, and then I forget about it. Do I know about game theory? Not really, to be honest. I mean, I'm aware roughly of the fields that's involved. But for example, I don't think I've ever taken a course or cracked open a textbook on game theory. But I can tell you about the greatest game, Chomp, in my opinion, because I like using this game to highlight the law of excluded middle. Also, I got my nephew to play this with me the other day, or not the other day. Sorry, we're not even in the same city. But last time I went to go visit my parents, and we were out to dinner, and my nephew, I told him how to play this game, and then I kept beating him. And I was trying to help him. I was like, well, think about, if, he'd point to a move, and I'm like, well, if you do that, like, which box will I color? And then he was like, oh, man. So then, of course, I told him we went through just a 2x2 board. Maybe I should explain the game before I tell this whole story too. But we went through all the possibilities of a 2x2 board together. And then, of course, he immediately, once I showed him that there's a winning strategy, he immediately was like, Mom, you got to play with me. And then he's like, I'm going to be player blank. I'm not going to tell you which is the player that wins, because we're going to find out in a second. Okay, so this is a bar of chocolate, Dubai chocolate. And this bar is poison. And okay, I'll label this so that chat can play with me. And and whoever the way that the game works is you pick a square, say this one, and then you have to eat everything down and to the right. So this whole like 2x4 thing would disappear, and then whoever is forced to eat the poison loses. So I don't know, chat. Do you want to go first, or should I go first? What do you think? Whatever I hear people say first is what I'll go with. Wow, stream's pretty laggy. How about like D6? Okay, so chat's going first. Okay, so a rod takes D6. Okay. Chomp fish 16. Is there actually? Okay, I'm pretty sure that's just a joke, but I'm sure that someone has also made Chomp engines 100%. So, okay, I will eat this one. So all of these go. Okay, chat, it's your move next. The Bernoulli thing. I don't really want to do this problem. Have you been working on it? I mean, I undoubtedly there's a proof. I think there's a proof on Wikipedia. I would say if you're still working on it at this point, you should probably just look up the proof. Oh, did it already give up that there's a winning strategy? Dang. Yeah. Well, someone, I mean, whoever picks the next move, the next move that I see is the move I'll go with. It doesn't have to be a rod. So, someone else can pick the move. I mean, for example, breaking myth. You asked about game theory, so I'd encourage you to put in a move. Can the hive mind of chat beat me at Chomp? I guess while I'm waiting for people to make moves, maybe I can think about Bernoulli again. But there were some other conditions, right? Wasn't this conditional? Like, didn't this held for like? There was this inequality. Oh, you don't understand the rule? So breaking mess. So Arad picked this square first, right? So everything down and to the right had to be eaten. So that got eaten, right? And then it was my turn. So I picked this square, and I had to eat everything down and to the right, and so I had to eat all of those, right? And then now, chat, it's your turn again. And so you have to pick somewhere to go. That's okay, Boris. That's the most acceptable excuse. So now you need to pick a different square, and wherever you go, yeah, you got to eat all down and to the right. You just don't want to get green. You want to force me to eat the green poison square. Wow, that's a fun idea for a coding project, though, Boris. Maybe. Oh my God, I almost shouldn't say this on stream because I'll need it to get a job. Maybe I'll, as a way to teach myself reinforcement learning. B2, okay. Breaking Myth picks B2. Ah, but you should have paid attention to what Arad said. So you pick B2, so everything down and to the right gets eaten. Maybe you missed Arad's message in the chat because now on my move, I'm going to pick 2. So I eat everything down and to the right. Oh, wait. Oh, sorry. Ah, aha, thank you. Okay. Sorry, Breaking Myth. That was my bad. I can't count. You're right. Okay, you picked B2. Nice. Okay, so everything down and to the right gets eaten. That was my bad. Sorry about that. Okay. Okay. I know that there's some way. Now I got to think carefully about this. Let's see. If I go here, there. Yeah, okay. I think I'm gonna eat, I'm gonna go here. I'll eat this one. Well, Arad, not in general, unfortunately. Not in general, unfortunately. In this specific configuration, when you have 2 wings, I couldn't remember which way it is, but so there are like certain board configurations that are solved. But I'll say something. I'll say something in a minute. But it's back to you, chat. I think I win. I think you guys are screwed no matter what. I'm pretty sure I win. But yeah, Matthias, this Bernoulli thing, there was some condition on X, right? Like, there were several different versions of these, just for the sake of it, A3. Okay, A3, boom. Okay, A3, right? So then I'll eat this one. Yeah, and now you guys are cooked, right? Whether you take B1 or A2, I'll take the opposite, and then you're forced to eat the poison chocolate and you die. Wow, murdered all my followers on stream. That's how it ends. Okay, so so this is a game, and one might be interested then to solve the game, right? So certainly you could imagine if you actually had to play this for real in real life, and want to avoid eating the poison piece of chocolate, you would really like to know if one player has a winning strategy, and more importantly, you'd like to know if that winning strategy, what that winning strategy is specifically. So it turns out that actually player 1 always has a winning strategy. How do we know? Well, suppose this is just like an ambiguously dying eating chocolate doesn't sound so bad. I mean, there's worse ways to go. So suppose we have a board of any size, right? An n by n board, some arbitrary n by n board. And suppose So it turns out there's actually a theorem, because this is a two-player game without where one player has to lose. There's a theorem that says that one player has to have a winning strategy. So the question is just, is it player one or is it player two? Well, suppose that player two had a winning strategy, right? So that means that no matter what player one does, player two has a sequence of moves that inevitably leads to a win. So imagine that player one, as in our game, by the way, begins with the bottommost corner. They take just this one square. Therefore, player two must have a sequence of moves beginning with some arbitrary other square, say over here, that then leads to them winning the game, where, depending on what player one does, of course, but they have a path through. However, notice that player one could have actually just picked this square to begin with. And so therefore, actually, player one has a winning strategy, because if player two had this winning strategy that starts at this square, actually player one could have just chosen that square, followed that same sequence of moves. So this is an example of a kind of proof. It's a strategy stealing proof that arises in game theory. Okay, great. So now we know, hey, player one has a winning strategy. The problem is, buried somewhere in these arguments is the fact that I have used the law of excluded middle, which says that for all propositions, either P or not P. So D6, C5, B4 is, well, that is a sequence of moves, right? But a winning strategy is actually essentially an entire set of games where you can always pick. So it's an entire set of sequences, right? Because you don't know what player two is going to do. So by the way, I talked about the 2x2 board, how I taught my nephew the winning strategy there, right? So let's look at the 2x2 board. So what is a winning strategy? So we'll go A, B, 1, 2, right? So basically we just enumerate, we can enumerate all the games, right? So we'll have like player 1, player 2, player 1, player 2, player 1, player 2, and we'll see, okay, the games aren't going to go that long, right? So does player one always have a way that they could win? So what are the possibilities? Well, player one could pick B1 to start, for example, right? If they picked B1 to start, maybe I'll make a couple games. Right? If they pick B1 to start, well, that's a pretty bad move. Well, I mean, there's different ways, right? So they go B1. It's a pretty bad move, because then player two is going to go A2, and then player one loses. So we could put an L here, right? So player one can definitely lose, right? What if player one, and then we see it's totally symmetric, like if player one went A2, well, then there's, again, there's only one choice for player one that doesn't lose. It's this. Boom. So player one can definitely lose. The only other possibility is that player one starts off with B2, right? And so now if player one starts off with B2, this is our like poison square here, there's actually two possibilities. There's two possibilities for what player two could do. They could either go B1, or they could go B1 or A2, but then of course player one just makes the opposite choice. right? To pee or not to pee. Exactly, Boris. Exactly. Wow. I'm going to steal that one from you. Yeah. So we can see that there's still, so in the setup, definitely there's still ways for player one to mess up and to fumble it. But there is at least one way. In fact, there's even more than one way. Well, of course, the possible games depend on what player two is going to do, right? So the point of saying that that player one has a winning strategy just means no matter if player one starts with a certain move, no matter what player two does at every next turn, there is some sequence of moves player one can make in response, which will lead them to victory. And the two, any two games could look very, very, very different in their sequence, in their sequences of moves. Yeah. But yeah, what was I saying? Yeah, but the point is, player one always has a winning strategy. Here's the problem though. With all of this, and this is why I like Chomp. It's an example. We depend somewhere in the argument we end up using the law of excluded middle. What does this mean? So player two should just go A1 and get it over with. Wait, where? Yeah. Well, not necessarily, right? And here's exactly why. Here's exactly why player two should not do that. Because we use the law of excluded middle, this is an example of what's called a non-constructive proof. So that is, we know, right? What this proof tells us is that player one has a winning strategy. But it does not tell us anything about what that winning strategy is. In fact, this argument doesn't even tell us what player one's first move should be. So we have no idea. All we know is that abstractly, player one has a winning strategy. And this is totally open. Like we have no idea for a general M by N board. We have no idea how to solve an arbitrary board. Of course, certain board shapes have been solved, right? Like probably N by N is solved, I would guess. And certainly with a computer, any one fixed board size, you can just brute force it. However, supposing you've solved all board sizes for M up to 100 and N up to 100, all possible combinations, this tells you absolutely nothing about the board sizes beyond that. Well, I shouldn't say absolutely nothing. Again, there's probably some theorems you can say, well, boards of a certain kind of shape, we could use induction, but the general case, wide open. So, and certainly, even for a small board like of this size, it's already pretty difficult to remember the strategy. It's not like there's a very well-defined pattern. And never mind a slightly bigger chocolate bar. You're basically screwed. So this is sort of my argument about, I like to give this an example as to why people should care about constructivism and constructivist proofs, because, for example, this highlights the difference between a constructive proof and a non-constructive proof, right? I mean, the non-constructive proof is effectively useless if you had to actually play this game. I mean, yes, that okay, given the choice, like if I pick player one, there is a winning strategy, but I mean, already on a board this size, like good luck actually figuring it out. It seems to be, more or less a toss-up whether you'd actually win it or not. So I guess an interesting question would be what proportion of games, what proportion of games actually do you win? Because wouldn't it be interesting if, so let's say no, you'd think they'd have to be, you'd think statistically player one would have to, I don't know. Wow. Kind of makes me want to do like a little coding project for Chomp. Interesting. Okay. Yeah. Well, that's that's about that. So I think that's where I'll end office hours for today. Um, will I eventually do the Bernoulli's inequality for Matthias? I don't know. I don't know. Winning strategy, is there something like that? Not sure I understand the question. For certain games, there are winning strategies, and definitely a winning strategy exists for. Yeah, I mean the proof's here. The proof's here right on Wikipedia. Yeah. Chomp AI might be a good idea, actually. Yeah. Maybe that's what I'll try to do. Maybe I'll try and code up my own little Chomp AI thing, and then I'll get a job as a quant making $1 billion a second. And then I'll retire at 45, and then I'll just hang out on a beach all day publishing random papers about nonsense. Until then, go prove some things. I'll go prove some things. We'll produce a lot of proofs, and we'll meet back here